Hubble has been in space for over 34 years, and its mission has been an incredible success. Although it wasn't originally designed to observe objects within our solar system, it has managed to do so throughout its journey, capturing extraordinary moments that would have otherwise gone unnoticed. Not every planet has a dedicated mission, and there's much more to see in our solar system beyond just the planets. Let's embark on a journey through our cosmic neighborhood, venturing from Earth to the farthest reaches of the solar system, exploring remarkable objects you might never have heard of, as revealed by Hubble's keen eye. We'll begin our grand tour close to home with our immediate neighbor, the Moon. Due to the Moon's large apparent size in our sky, Hubble cannot capture its entire surface in a single image. Moreover, other missions, such as NASA's Lunar Reconnaissance Orbiter, provide far better images of the Moon, thus Hubble's time is better utilized elsewhere. However, in 2012, Hubble captured an intriguing image during a special event: Venus passing in front of the Sun. Why observe the Moon during this event? Scientists used it as a massive mirror to detect subtle variations caused by sunlight scattering through Venus's atmosphere. These variations revealed details about the atmosphere's chemical composition. Although Venus's atmospheric composition is already well known, this experiment tested whether the light scattering method produces accurate results. Hubble frequently applies this technique to study exoplanet atmospheres by observing distant stars as planets transit in front of them. Since the Sun is too bright for Hubble to observe directly, using the Moon as a reflector enabled scientists to obtain the data they needed. While capturing the entirety of the Moon poses challenges for Hubble, the same is not true for Mars. Hubble often observes Mars, offering a full view of the planet's disk, something orbiting spacecraft can't always achieve. These images provide valuable insights into dust storms, seasonal changes, and other weather phenomena. Such information is crucial for planning rover operations and building a comprehensive understanding of Martian weather for future predictions. In one time-lapse, a global dust storm envelopes the planet, obscuring surface features. Mars's two small moons, Phobos and Deimos, can be seen zipping around the planet in the background, their rapid motion especially noticeable in the 42-minute sequence. Another time-lapse focuses on Phobos, the larger and closer of Mars's moons, showing its movement over just 22 minutes. Phobos completes an orbit around Mars in only 7.5 hours, making it the only moon in the solar system to orbit faster than its planet's day. As we leave the inner planets behind and approach the first of the gas giants, we encounter the asteroid belt, a fascinating region filled with objects worth studying. Among them is the curious asteroid 6478 Gault, a misleadingly named celestial body that has captured Hubble's attention. You might be surprised to learn that this object, which clearly resembles a comet with its twin tails, is actually an asteroid known as Gault. This asteroid resides in the asteroid belt and was imaged in 2019. So why does it have a tail? Scientists believe the answer lies in a phenomenon called the Yarkovsky, O'Keefe, Radzievsky, Paddock, YORP effect. Solar radiation exerts a small but steady force on irregularly shaped bodies, and under the right conditions, this can gradually increase their rotation speed. In Gault's case, its 3.5 km wide body has been spinning faster over time and now completes one rotation every 2 hours, the upper limit of what an asteroid can endure. This rapid rotation generates centrifugal forces that are stronger than the asteroid's gravity, causing loose material to be ejected into space. These ejections form the tails, and over time, Gault will likely disintegrate entirely. Like many other asteroids and comets, Gault isn't a solid rock but a fragile rubble pile held together by weak gravitational forces. The asteroid belt, with its chaotic population of 1 to 2 million asteroids larger than a kilometer and countless smaller ones, is a dynamic region. To illustrate this, let's examine P/2010A2. At first glance, it appears to be a typical comet. However, a closer look at its nucleus reveals an unusual filamentary structure. Surprisingly, this is not the comet's nucleus. It isn't even a comet. What we're seeing is an extraordinarily rare event, a collision between two asteroids. The X-shaped structure near the nucleus consists of debris from the impact, with rubble being ejected in 4 directions. Some of this material is pulled back toward the center of mass by the faint gravitational pull, while particles in the tail have escaped entirely. Despite the occasional chaos, most asteroids in the belt follow relatively stable, circular orbits around the Sun. But if an asteroid strays too far from this path, as comets do, it risks encountering a far more powerful gravitational force. Jupiter, often called the solar system's vacuum cleaner, is a dominant force in this region. Its immense mass accounts for nearly 3/4 of all the matter in the solar system outside the Sun, giving it a gravitational influence that shapes the fate of nearby objects. A striking example of this occurred in 1994 when the 2 km-wide comet Shoemaker-Levy 9 ventured too close to Jupiter. The planet's gravity not only captured the comet but also tore it apart, breaking it into several fragments. By the time the fragments impacted Jupiter, they were already scattered, marking the first-ever direct observation of an extraterrestrial collision. Interestingly, Shoemaker-Levy 9 had been captured by Jupiter roughly 2 decades earlier and orbited as an active comet, a phenomenon also observed for the first time. However, its orbit eventually brought it perilously close to Jupiter's surface. The resulting tidal forces shredded the comet, and just a year later, its fragments collided with Jupiter at an astonishing speed of 60 kilometers per second, over 210,000 kilometers per hour. The impacts on Jupiter generated fireballs reaching temperatures of over 23,000 degrees Celsius, soaring an astonishing 3,000 kilometers above the planet's limb. The most significant impact left a dark spot spanning 12,000 kilometers, roughly the size of Earth, and unleashed energy equivalent to 6 million megatons of TNT, more than 600 times the power of the world's combined nuclear arsenal. While other impacts have been less dramatic, they've been observed and photographed, lending credibility to the theory that Jupiter acts as a cosmic vacuum cleaner, shielding the inner planets of the solar system from catastrophic collisions. Beyond its immense gravitational influence, Jupiter offers ethereal phenomena that captivate astronomers. For instance, Earth isn't the only planet to experience auroras. While auroras are visible to the naked eye on Earth, they are actually brightest in ultraviolet light. Thanks to the Hubble Space Telescope's ability to detect ultraviolet wavelengths, we've been able to closely study these dazzling displays on other planets. Jupiter's auroras are the easiest to observe, as the planet is not only the largest and closest of the gas giants but also has a powerful magnetic field and intense radiation that generate incredibly bright auroras. In 2016, during the Juno spacecraft's journey to Jupiter, scientists seized the opportunity to measure solar wind en route and study its impact on Jupiter's auroras using Hubble. This collaboration allowed Hubble to monitor Jupiter almost daily for several months. The findings revealed auroras hundreds of times more intense than those on Earth, with a radiant power of 100 terawatts. Remarkably, unlike Earth's auroras, which appear sporadically during solar storms, Jupiter's auroras are continuous. This discovery suggests that Jupiter's auroras are not solely driven by solar wind. Data from Juno indicates that the planet's fierce radiation belts supply charged particles into the atmosphere via magnetic field lines. Additionally, alternating currents, rather than direct currents, within the magnetic field explain the aurora's radiant energy, a phenomenon that wouldn't occur with direct current energy transfer. After exploring Jupiter itself, let's shift our attention to one of its most intriguing moons, Europa. This icy satellite may potentially harbor the closest extraterrestrial life to Earth. Hubble has captured Europa in impressive detail, considering the vast distance. Europa is a major moon of Jupiter and one of the prime candidates for life in the solar system, not on its surface but beneath it, within a subsurface ocean of liquid water. Europa's proximity to Jupiter results in extreme tidal forces, causing what is known as tidal flexing. This process generates heat, which scientists theorize keeps the ocean beneath Europa's icy crust warm enough to remain liquid. Various missions have sought evidence to confirm this ocean's existence, with Hubble playing a surprising role. While spacecraft like Galileo and Voyager captured higher-resolution images during their close flybys, they lacked Hubble's ability to observe ultraviolet light. Hubble has detected what appeared to be plumes of water vapor erupting from Europa's surface. If confirmed, this volcanic activity would suggest a liquid interior mantle, further supporting the ocean hypothesis. Since the initial observation, many more plumes have been detected on Europa. Hubble's capabilities were also utilized to identify salts on the Moon's surface. While most missions rely on infrared imaging to study planetary surfaces, since many key emission bands of substances are in the infrared spectrum, sodium chloride, common salt, is primarily visible in the visible light spectrum. This limitation meant that Galileo missed detecting these salts. However, Hubble, observing invisible light, confirmed the presence of sodium chloride spread across Europa's surface. This discovery suggests the salts likely originated from the underground ocean, carried to the surface by the plumes, and deposited there. The presence of sea salt deposited on Europa is an exciting prospect because it implies the ocean floor could host hydrothermal activity. On Earth, hydrothermal vents are teeming with life, making this a promising avenue for further investigation. Unfortunately, sending a submarine mission to explore Europa's hidden ocean may still be a few decades away. Let's move on to the next stop in our journey through the outer planets, Saturn. After the Cassini mission ended in 2017, Saturn has been without a dedicated spacecraft, leaving the Hubble Space Telescope as our best tool for studying this gas giant. Hubble frequently observes Saturn, monitoring phenomena such as atmospheric weather and seasonal changes. Cassini studied Saturn for only half a Saturnian year, so Hubble now plays a crucial role in filling in the gaps in data. Among the most striking events Hubble has observed are massive storms stretching thousands of kilometers across Saturn's surface. In addition to its scientific contributions, Hubble also captures breathtaking images of the Saturnian system, showcasing its beauty. Here are some of the most stunning examples. As we near the end of our tour, let's visit the first of the icy giants, Uranus. Like Jupiter and Neptune, Uranus has storms visible on its surface and even aurora near its magnetic poles. Interestingly, Uranus's magnetic poles don't align with its rotational axis, adding to the planet's quirks. Uranus's rotational axis is tipped so dramatically that it appears to roll along its orbit, setting it apart from the other planets in the solar system. This unique tilt also means solar eclipses from Uranus's moons are exceedingly rare. The first recorded instance of a moon's shadow crossing Uranus occurred in 2006, as the last alignment in 1965 predated telescopes capable of observing such distant events. During this historic observation, Hubble captured a moon's shadow transiting the planet's surface and also provided a detailed view of Uranus's atmospheric bands. Since that time, continued Hubble observations have revealed seasonal changes in Uranus's atmosphere over parts of its 84-year orbit. When one pole tilts toward the Sun, the atmosphere becomes lighter in color, forming a large cloud cap during the summer season. This feature dissipates as Uranus moves toward its equinox. Because Hubble is only 34 years old, it has observed less than half of a Uranian year, leaving much more to learn about the planet's seasonal dynamics. Finally, let's touch on an incredible discovery made by Hubble: Hippocamp, Neptune's smallest known moon. Without the telescope's capabilities, we might never have even known this tiny moon existed. The outer ice giants, Neptune and Uranus, have been largely overlooked by space agencies, with only a single close encounter, the Voyager 2 flyby in 1989. As a result, our understanding of these distant worlds remains quite limited. Without the observations from the Hubble Space Telescope, our knowledge would be even sparser. One of Hubble's major discoveries about Neptune came in 2013 when it identified a new moon, later named Hippocamp. While Hubble has discovered numerous moons, particularly around Jupiter and Saturn, Hippocamp stands out because it may be a fragment of Neptune's much larger moon, Proteus. Proteus, a 400 kilometers wide moon, bears evidence of a turbulent history, including massive impact craters measuring 50 to 100 kilometers across. One of these collisions likely broke apart Proteus, sending fragments into orbit around Neptune. Hippocamp, an irregularly shaped object about 35 kilometers long, is believed to be the largest of these fragments and orbits relatively close to its parent moon. As we near the end of our journey, let's take a closer look at Neptune itself. Although Hubble was not specifically designed for monitoring our solar system, in 2015, more of its time was dedicated to studying the ice giants, allowing for annual observations of these planets. This initiative has improved our ability to track seasonal changes in their atmospheres. One of the most striking features of Neptune's atmosphere is the presence of giant storms spanning thousands of kilometers. During Voyager 2's 1989 flyby, a massive storm, later called the Great Dark Spot, was observed, resembling Jupiter's Great Red Spot. However, unlike Jupiter's persistent storm, Neptune's Great Dark Spot has since vanished. New storms have formed and dissipated over the years, with the most recent one observed in 2018. This storm lasted several years but is now thought to have disappeared as well. Although data remains limited, scientists hypothesize that Neptune, like Jupiter, may have atmospheric bands traveling at different speeds. The interaction between these bands could give rise to vortices or storms where they meet. Once a storm forms, it drifts across the planet, occasionally crossing between bands. However, when it loses its power source, the storm gradually weakens, which seems to explain the transient nature of Neptune's vortices. Hubble is currently the only observatory capable of tracking these atmospheric changes, as storms on Neptune and Uranus are nearly invisible in most light wavelengths. Fortunately, Hubble can study these planets in the ultraviolet spectrum, providing unique insights into their weather patterns. And now, as you may have realized, we've reached the end of our journey with no more planets left to explore. Our tour of the solar system must come to a close. Before we wrap up, there's one more dwarf planet worth mentioning, a fascinating world beyond Neptune that Hubble has studied. You might be thinking of Pluto, but no, we're talking about 2007 or 10, also known as Gong. Surprised? That's understandable. This celestial body isn't exactly a household name, despite being the third largest dwarf planet in our solar system, trailing only Pluto and Eris in size. Like its better-known siblings, Gong resides billions of kilometers away in the Kuiper Belt. Although Hubble didn't discover Gong, it played a crucial role in revealing an important detail about it. Gong has a moon. This discovery wasn't made initially because the moon appeared faint in earlier images. However, recent research suggested its existence due to Gong's unusually slow rotation, taking about 45 hours to complete a spin. Most Kuiper Belt objects rotate in less than 24 hours, so scientists hypothesized that the drag from a moon's gravitational pull could explain the slow spin. By revisiting archival Hubble data, they confirmed the moon's presence. This discovery highlights an intriguing trend. Nearly all of the known dwarf planets in the Kuiper Belt have moons. This may be due to the region's low-speed collisions. Objects in the Kuiper Belt move slowly enough that fragments from impacts are more likely to remain gravitationally bound, forming moons. In contrast, in the asteroid belt, collisions are much more energetic, often flinging debris into space rather than allowing it to form moons. Identifying Gong's moon provides valuable data to refine our models of solar system formation. This seemingly small finding adds another piece to the puzzle of understanding our cosmic neighborhood. Reflecting on these discoveries, it's clear how instrumental Hubble has been in expanding humanity's understanding of space and our solar system over the past 3 decades. Hubble has achieved far more than anyone could have imagined, offering insights and images that will fuel scientific discovery for years to come. What's more, Hubble's mission isn't over yet. With proper care, it could continue operating until 2040, potentially outliving its spiritual successor, the James Webb Space Telescope, JWST. If you enjoyed this video, don't forget to give it a thumbs up, share it with your fellow space enthusiasts, and subscribe for more cosmic content. And as always, keep looking up, you never know what you might see. Until next time, stay curious.